Non-adiabatic flash examples, modernized control strategies. With 3 control degrees of freedom, the non-adiabatic flash unit provides a highly flexible platform for advanced process control. The introduction of heat input as a manipulable variable adds a new dimension to separation control, allowing engineers to regulate not only flow rates and pressure, but also thermodynamic equilibrium through direct energy manipulation. Modern distributed control systems, DCS, and advanced process control, APC platforms take full advantage of this flexibility. By integrating smart sensors, real-time modeling, and auto-tuning loops, engineers can design control strategies that optimize yield, energy usage, and separation performance, even under fluctuating feed conditions or variable utility availability. Example 1. Pressure, temperature, and vapor rate control. Controlled variables. Pressure, managed using a vapor outlet valve or back pressure control. Temperature, controlled via steam heat input to the flash vessel. Vapor flow rate, regulated using a flow control valve on the vapor outlet. Manipulated variables, heat input via steam valve, vapor outlet valve, feed flow used for level inventory control. Modern implementation, temperature control loop interfaces with a model predictive controller that adjusts steam duty based on desired phase equilibrium. Pressure is maintained via high-precision control valves with position feedback diagnostics. Smart vapor flow meters provide real-time data for controlling overhead recovery or product specifications. Application fit, used when vapor phase composition or purity is critical, e.g., light ends recovery upstream of compression. Excellent for systems requiring tight energy input control for cost or emissions management. Example 2. Pressure, liquid and vapor flow control. Controlled variables. Pressure, controlled via steam input or vent valve. Liquid flow rate, controlled to regulate product withdrawal. Vapor flow rate, controlled to match downstream demand or maintain split ratio. Manipulated variables. Liquid and vapor outlet valves. Heat input used to maintain pressure. Feed regulated for inventory via level control. Modern implementation. Integrated flow controllers handle both product lines. Pressure control uses a smart steam valve linked to a high-resolution pressure transmitter. Coordination between vapor and liquid loops is supported by APC logic to avoid overloading downstream units. Application fit. Best suited for intermediate separation where both phases are sent to downstream operations and must be controlled independently. Useful in swing mode plants or multi-grade production where product cuts vary dynamically. Example 3. Feed rate, liquid vapor flow ratio, and pressure control. Controlled variables, feed rate, adjusted based on upstream production or downstream pull. Vapor to liquid flow ratio, controlled via a ratio controller. Pressure, regulated by varying heat input or manipulating vent load valve. Manipulated variables, vapor valve or liquid valve in ratio loop, steam valve for pressure, feed flow via upstream cascade, level loop on the remaining product stream. Modern implementation, ratio control implemented through dynamic control blocks with digital supervision, e.g. if either stream fails, ratio loop suspends. Steam control integrates with utility optimization systems to maintain energy efficiency. APC models supervise overall operation and adjust set points for throughput and composition targets. Application fit, effective when process economics are linked to maintaining a consistent phase ratio, e.g., flashing to maximize vapor recovery or minimize reprocessing. Allows rapid switching between product specifications in flexible plants. Example 4, pressure, temperature, and vapor to feed ratio control. Controlled variables, pressure, maintained via vapor back pressure or reboiler duty. Temperature, regulated using direct steam input or heat exchanger outlet temperature. Vapor to feed ratio, controlled using ratio logic to maintain consistent separation behavior. Manipulated variables, heat input, vapor flow control, ratio loop, feed flow used for inventory regulation, level control on liquid product. Modern implementation, ratio controller logic integrated with predictive models for better stability under load swings. Smart heat exchangers or steam flow controllers are equipped with auto-tuning and predictive diagnostics. Real-time dashboards track key separation efficiency metrics, e.g. flashpoint phase split, product recovery. Application fit. Excellent for energy-sensitive operations and plants with frequent feed composition variation. Ensures process stability even during transitions between startup, ramp-up, and steady state. Advanced features in all examples. Modern control strategies often include the following across all configurations. Model-based validation. Digital twins simulate performance before implementation. AI-assisted tuning. Control parameters are automatically refined based on loop performance using cloud-based learning algorithms. Multivariable coordination. APC platforms supervise multiple loops to prevent interaction, improve constraint handling, and optimize energy use. Process safety integration. All steam and pressure loops are safeguarded via SI-S layers to prevent runaway heating or overpressurization. Summary. Non-adiabatic flash units offer a versatile platform for modern control, with 3 degrees of freedom enabling diverse configurations tailored to product quality, energy efficiency, and operational agility. Each example demonstrates how heat input, flow rates, and pressure can be coordinated to match process demands, product specifications, or optimization goals. The ability to simulate, deploy, and adapt these control strategies using modern DCS and APC systems, T-Systems turns the non-adiabatic flash into a smart, responsive, and economically critical unit in any advanced processing plant. Three-phase flash, modernized control strategy, and degrees of freedom. A three-phase flash separator is used in processes where the feed splits into vapor, aqueous, light liquid, and organic heavy liquid phases, such as in oil-water separation or primary treatment of multi-phase well fluids. The added complexity of an additional liquid phase demands a more sophisticated control strategy to manage not only the thermodynamic separation, but also interface control between immiscible liquids. In modern plants, these units are tightly integrated with digital instrumentation, smart control valves, advanced diagnostics, and remote visibility platforms, ensuring stable separation, safe interface levels, and optimized phase flow rates is critical to both production reliability and downstream process protection. Degrees of freedom analysis. The degrees of freedom F help determine how many independent control actions are available after accounting for process constraints. System configuration. 1 feed stream, 3 product streams, vapor, light liquid, and heavy liquid. Constraints. 2 immiscible liquid phases introduce 2 interface levels that must be maintained. All 3 phases are typically in equilibrium under a common pressure and temperature. DOF calculation. Text degrees of freedom equals text num of phase interfaces. Equals 4 text, 1 feed plus 3 products, minus 2 interfaces, math BF2. Thus, the system has 2 control degrees of freedom, enabling control of 2 strategic variables, e.g. pressure and feed flow rate, while the remaining streams are used for inventory regulation through interface control loops. Modern control strategy. To maintain robust separation and downstream compatibility, the 3-phase flash employs the following control configuration. 1. Interface level controls. Inventory loops. For upper interface, vapor light liquid, controlled by adjusting vapor outlet valve to manage vapor disengagement and pressure hold. Lower interface, light heavy liquid, controlled via heavy liquid outlet valve, e.g. water draw or brine outlet, to maintain a clean split between immiscible layers. These loops ensure that water doesn't contaminate the organic phase or vice versa. The separator operates within mechanical limits. Slugging and carryover are avoided. 2. Active control degrees of freedom, strategic variables, example configurations. Feed flow rate and pressure control. Feed flow rate is set to match upstream availability or downstream demand. Pressure is maintained using a vapor outlet valve or back pressure regulator. Both light and heavy liquid levels are managed via level controllers. Temperature and pressure control if heated. Heat input, e.g. steam or hot oil, may be used to optimize separation via viscosity or density differences. Temperature is controlled using a jacket or external heat exchanger. Pressure is held steady to maintain phase equilibrium. Advanced instrumentation and automation. Smart interface level transmitters use guided wave radar or capacitance probes calibrated for multi-phase service, capable of distinguishing clean phase boundaries even with emulsions. High-speed digital controllers implement fast PID or model predictive logic to stabilize interfaces, especially under slugging or transient conditions from upstream. 3D separator models and digital twins, used to simulate behavior under changing feed compositions or startup, shutdown scenarios. Automated slug management. Some systems use AI-assisted diagnostics to identify slug flow and adjust outlet valve profiles to prevent downstream surges. Control integration. Safety system coordination. High-level alarms, e.g. vapor carryover or interface collapse, trigger ESD or upstream trip signals via SIS integration. Downstream protection. Phase control ensures that incorrect routing of water into hydrocarbon trains or hydrocarbon into water treatment systems is prevented. Remote and predictive monitoring. Interface trends, phase densities, and valve wear diagnostics are monitored remotely and fed into predictive maintenance systems via CMMS integration. Summary. The three-phase flash separator, with its 2 degrees of freedom and three-phase inventory challenge, is a critical control-intensive unit in multi-phase processing environments. While its thermodynamic behavior is inherently more complex than two-phase systems, modern instrumentation and control systems enable precise interface management, process stabilization, and high reliability. With advanced diagnostics, digital twins, and integrated safety protections, the three-phase flash evolves from a basic separator into a smart, responsive system that safeguards downstream units, improves separation efficiency, and ensures compositional integrity of products. Countercurrent cascade columns, modernized control strategy, and degrees of freedom. Countercurrent cascade columns are widely used for gas-liquid or liquid-liquid mass transfer operations, including absorption, stripping, and solvent extraction. Their performance depends critically on the interaction between upward and downward flows, temperature gradients, pressure stability, and phase contact efficiency. In modern chemical plants, these columns are digitally managed with precise instrumentation, real-time optimization, and multivariable control strategies to maintain composition, throughput, and energy balance under a variety of operating conditions. Degrees of freedom analysis. In control system design, degrees of freedom, DOF, define how many process variables can be independently controlled given the system constraints. System configuration. 4 streams, 2 inputs, typically gas and liquid feeds, and 2 outputs, typically gas and liquid products, 1 gas-liquid interface, single mass transfer zone, text. Degrees of freedom equals number of streams, text number of interfaces. P equals 4 minus 1 equals math 3. Thus, the system allows 3 actively controlled variables, while the 4th stream is typically used for inventory or level control to maintain mass balance within the column. Key control objectives. Modern control systems for cascade columns are designed to meet 3 simultaneous goals. 1. Maintain column pressure. 2. Regulate one feed or product flow rate. 3. Control product composition, typically top or bottom. The 4th variable, usually a bottoms or overhead flow, is then used for level control or interface management. Example 1, good composition control. Control loops. Liquid feed flow rate regulates throughput. Column pressure, controlled via overhead vapor flow or pressure control valve. Bottom product composition, controlled via adjustment of gas input, manipulates internal mass transfer driving force. Level control adjusted via bottoms outlet valve. Modern implementation, online composition analyzers, e.g. NIR, FTIR, conductivity, feed directly into composition control loops. Cascade control between analyzer and flow valve for gas input improves responsiveness. APC systems coordinate pressure and composition loops to avoid interaction. Performance. Fast, localized adjustments, strong response to disturbances, excellent quality control at column bottom. Example 2, poor composition control. Control loops, liquid feed flow rate, column pressure. Controlled as before. Top composition, like controlled via gas input from the bottom. Level control, bottoms outlet valve. Modern assessment. Long delay between gas flow change and composition response at column top due to upward residence time. Model-based control or predictive logic would be needed to compensate for this lag, but performance is still degraded. Recommendation: avoid long-distance control paths. Use direct action, e.g., adjust top flow for top composition when possible. Example 3, bad composition control, control loops, gas feed flow rate, column pressure. Bottom composition, controlled via liquid feed rate, top of column, level control, bottom's outlet valve. Modern assessment, extremely poor response due to long delay from top to bottom, high risk of oscillations and poor disturbance rejection. Even advanced MPC would struggle without real-time composition prediction and intermediate measurement points. Recommendation: avoid any configuration where the manipulated variable is located opposite the control point within a tall column. Use local controls. Modern GER, modern instrumentation and enhancements. Smart flow meters and control valves enable precision flow regulation with diagnostics, position feedback, and travel monitoring to ensure accuracy. Pressure and level transmitters with deadband compensation ensure fast response to tight set points and dampen noise in high-pressure columns. Composition estimators and soft sensors, used when online analyzers are unavailable or delayed. Machine learning models infer composition from easily measured process variables. Multivariable APC integration, coordinated control of pressure, temperature, and flow to optimize separation efficiency while reducing energy consumption and minimizing interaction. Digital twin and predictive validation. Dynamic simulations evaluate control performance under disturbances such as feed variability or ambient temperature changes. Control strategy testing under simulated startup, turn down, or load swing scenarios. Predictive alarms trigger if composition, pressure, or level is trending toward constraint limits. Summary. Countercurrent cascade columns require precise control to ensure effective separation and steady production. With 3 degrees of freedom, modern control systems can manage throughput, pressure, and composition, so long as control loops are thoughtfully assigned and dynamically balanced. Best performance is achieved when manipulated variables directly affect their corresponding control points. Delays are minimized through smart valve placement and predictive control. Strategic variables are prioritized in APC or digital twin models. Through these enhancements, the cascade column becomes not only a mass transfer device, but a digitally optimized unit operation, contributing directly to plant profitability and stability.